All right. Now it's time to kick off our marathon of talks with a truly exceptional guest, Neal Ford. Many attendees from various countries have come to our summit for the unique opportunity to engage with him in person. Neal is currently the director, software architect, and Meme Wrangler at ThoughtWorks. Neal is renowned internationally as an expert in software development and delivery, particularly at the intersection of agile engineering techniques and software architecture. He has authored numerous magazine articles and books, including titles like Building Evolutionary Architectures, Functional Thinking Paradigm Over Syntax, The Productive Programmer, Fundamentals of Software Architecture, the hard parts, and Software Architecture Metrics. Wow, what a list. He has also delivered dozens of video presentations and spoken at countless developer conferences worldwide. Neal's diverse range of topics covers software architecture, continuous delivery, functional programming, cutting-edge software innovations, and even includes guidance on improving technical presentations with a business-focused approach. His primary consulting focus revolves around the design and construction of large-scale enterprise applications. Today, Neal will share his insights on the intersection of architecture, fitness functions, and metrics. And Neal, the stage is yours.
It's great to see everyone's happy faces this morning. And I've been asked to come here and talk about this subject that I wrote about twice. Actually, the first edition of the book that defined this came out in 2017, and then the second edition came out just last year. I'm here to talk about this intersection of fitness, function, and metrics, but a little bit of background is probably necessary here. Two of the authors of this book, myself, I took a very indirect route to computer science. My first major in university was journalism, which is probably why I've written 10 books. That's where the journalism part comes out. But I was, for a while, really interested in the hard engineering, like mechanical engineering. And in fact, I got my two-year degree in physics and started into the engineering curriculum until I realized I do not want to do that the rest of my life. Way too much detail and math. And when you look at mechanical engineering, what you learn is they have a tremendous amount of very deep analysis they can do using math and calculus, and it's truly amazing. In fact, the dynamics class in mechanical engineering is known as the class that is its own prerequisite, because you have to take it once and fail it, and then take it again, and you'll eventually pass it because it's so difficult. So that's some of my background. The other background that's interesting is Rebecca Parsons, one of my co-authors. She was the one who had the original idea of this idea of an architectural fitness function that I'll define in just a second. So here's what I'm going to talk about briefly today, a brief definition of this idea and then the mechanics around it. But what I really want to dig into is how can you effectively use metrics in software architecture to try to get closer to a proper engineering discipline like something like mechanical engineering. So we defined evolutionary architecture in our first edition as one that supports guided incremental change across multiple dimensions. I'm only going to talk about the guided part of this definition today, and this is where this idea from Rebecca came from. This is an example of what I refer to as a metaphorical mashup. Occasionally what happens is you take an expert in one field and set them down in front of a completely different field and say, hey, can you do something interesting here? And this is exactly what Rebecca did, because she spent a fair amount of time in the evolutionary computing world designing genetic algorithms. And a genetic algorithm is one where you produce an algorithm and it produces a result and then mutates itself and produces another result and mutates itself and continues doing that until it reaches some stopping state. One of the tools in that world is this thing called a fitness function. It's a way to kind of guide the output and how it mutates. So maybe you've noticed that if you give it small numbers, you get more desirable outcomes, and you want to nudge it towards small numbers, that's what a fitness function is used for. So for example, if you were trying to solve the traveling salesperson problem using a genetic algorithm, your fitness function would be the length of route because that's the thing you're trying to minimize. I want the shortest one of these, and so things that give me shorter routes are better, and I'm trying to nudge it to get it to do that. What Rebecca did when she got to software architecture was she started noticing that to really evolve architecture, you need certainty that you haven't broken important things. So one of the things I will keep coming back to today is this idea of actual engineering in software. And we keep trying to metaphorically take other kinds of engineering and apply it to software. So one of the things that we're kind of seeking, in fact, I had a conversation about this last night, is the same kind of mathematics mechanical engineers have, but applied to software development, where we can look at software and mathematically analyze all the parts and understand the stresses and the structure. And I'm going to argue today that I don't think that can exist for reasons I'll get into. This is the mechanics of how do you take something that has hundreds or thousands or hundreds of thousands of moving parts, any one of which can change at pretty much any time. You need to do engineering and software two fundamental things: the ability to do incremental change and get fast feedback to say, did that small change break anything? This is not a new idea. Kent Beck pioneered this idea with extreme programming back in the 1990s, but I believe that's the seed of our kind of engineering, and I'll show you what I mean by that. So this idea of a fitness function is a validation mechanism, but for architecture characteristics, not for our problem domain. The problem is that our architecture characteristics, all the ilities, things like scalability and elasticity and security and modularity and deployability, there's not a single tool or framework that can tell me all those things. And instead, fitness functions are a combination of many things. Monitors to measure things like performance or scale or elasticity. Chaos engineering is a great example of how to test and stress test availability and reliability at the architecture level. Unit tests, there's special unit testing libraries that let you test your architectural structure. So if you design a layered architecture, you can validate that no one's cheating on your layers with tools like ArcUnit or NetArcTest. And of course, software metrics and a whole bunch of other things that have been created over time as well. And one of the questions I often get is, can you give me an example of a very simple fitness function? And here's a great example of one of these that I use sort of as my hello world fitness function, because it's one of those places where the universe is actively fighting you to try to do the right thing. You're trying to do the right thing, and the universe is conspiring against you to do the wrong thing. Because one of the things you want to try to avoid in component-based systems are cyclic dependencies between your components. That's where one component talks to another one, which talks to a third one, which talks to the original one again. This is considered bad because now it's hard for me to reuse one of those components without taking the whole rat's nest with me. And of course, if these get cyclically bound up with other components, this is where you get the big ball of mud in software. Just as a little side note, some of you may have heard this term. I always heard it as bit rot, but Wikipedia seems to think it's called system rot. It's this idea that a piece of software that's old has to be terrible. That somehow, that over time, software sort of rusts or erodes or degrades all by itself. This is part of system rot. Is if you don't pay attention to this, a single cyclic dependency is not fatal to your code base. Hundreds of them make your code base unmaintainable. But the problem with this is, how do you prevent this from happening? Because as you're typing along in your favorite IDE and you reference some class that you've never referenced, what does your IDE do for you? Pops up a dialog that says, do you want me to auto-import that for you? And you swat that dialogue away as fast as you possibly can. You haven't read that dialogue in years. I'll give you a clue. They replaced the text on that dialogue with a nursery rhyme 3 years ago, and you never realized it because you haven't read that thing in forever. because you know the thing to do when it shows up is swat it away and get back to work. And most of the time, that's great. But every once in a while, it's doing this to you. How do you prevent that from happening? Well, you could pair with every single coder every day, but you don't scale enough to do that. What you do is build a fitness function to guard against this. This is automated governance in software architecture. I don't want cycles in my code base, but I don't want to make people stop using Code Insight and the auto imports, and so I'll protect against cycles in my code base. There are actually a number of metrics tools that look for cycles and will fail tests if those cycles show up. Oh, look, it's metrics. It's a metrics package. This is an application of metrics as this idea of an architectural fitness function. As I said before, this is really a validation mechanism. So when you think about structural design in software architecture, there'll be a lot of discussion about this over the next 2 days. We can really split that into 2 activities. One of them is defining and analyzing the architecture characteristics. These are the capabilities of the system: performance, scalability, elasticity, security, etc. And then we have the problem domain. This is the thing that we're writing software about, the reason we're writing software. And you have to analyze both of these things, because if you just design for the domain, you may not have the kind of capabilities you need to be successful. Given that these are the 2 kinds of structural design, we need ways to validate if we make a change to something, have we broken anything? Well, it turns out we have fantastic validation mechanisms for our domain. We call these unit tests and functional tests and user acceptance tests. And in fact, if your company is big enough, you have an entire department called QA that does nothing but make sure that you haven't regressed and broken your domain as you evolve your software. What we need is a similar mechanism to architecture, for our architecture characteristics, and that's what these architecture fitness functions are. You can sort of think of them as unit tests for architecture characteristics. Now, one of the common questions I get is, well, this sounds like a great idea, but I want to download some fitness functions for my architecture. Where can I go find a great framework that has a bunch of these things in it? It's like asking someone that, oh, I see that you've written an insurance application. Can I have all the unit tests from that insurance application? Because I'm writing an insurance application too, and I'll just use all those unit tests to build my insurance application. It doesn't quite work that way. And the same is true for these fitness functions. They are really, really specific. And that, it turns out, is a really important theme here. So one of the things that Mark and I distinguished in our Fundamentals of Software Architecture book as we were talking about this is this idea of a composite architecture characteristic. One of the things that I will argue here is that you really want to boil these characteristics down to objectively measurable things. Because if you can get it down to something that's objectively measurable, you can validate whether it's that or not. The problem is you have a lot of architecture characteristics like this, maintainable. What is the single value that tells me if my architecture is maintainable or not? There's not one. This is an example of what we call a composite architectural characteristic, because it's composed of other architecture characteristics that you can, in fact, objectively define, like cyclomatic complexity. I'll talk about that a little more in just a second. Things like naming conventions lead to maintainability, and you can objectively measure, are we adhering to naming conventions. Things like immutability can be measured with tools like ArcUnit, and that leads to more maintainable code. Things like controlling coupling, knowing what should be coupled to each other and preventing things that shouldn't be coupled from each other to each other, using tools like ArcUnit or NetArcTest, etc. Those are all ways to validate maintainability. And here's an example that shows that this is not a new idea. This actually is something from my distant past. I was working for a while at an organization. It was an insurance company. I was working as a consultant, and they were concerned about the quality of the developers they were hiring, and they were afraid they were producing really terrible code. And so this one particular task had one server-side piece in Java, one client-side piece in JavaScript, and this is a very inexperienced developer, and there was something that needed to apply to all 50 states in the US. So they ended up writing some code, and this is the good version of that code. If state equals Georgia, then a whole bunch of lines of code. Else if state equals Alabama, then a whole bunch of, for all 50 states. So it created this nice, long, massive method. But the architects on that project ran a cyclomatic complexity check on the code. Cyclomatic complexity is a well-known method that gives a numeric measure for how complicated your code is. And they had set a threshold for their code at 50. And I'll tell you exactly where they got that number. There's a metrics tool in the Java world that still exists called crap4j. It looks at the combination of code coverage and cyclomatic complexity to determine how crappy your Java code is. And in their estimation, if your cyclomatic complexity ever gets higher than 50, no amount of code coverage will make that code not crappy. And so that was their ultimate upper threshold, which is monstrously high. The industry says less than 10 is probably okay. I usually shoot for less than 2, like 1.5 or 2. But so they set a threshold for 50, and this developer tried to check this code in, and it failed that cyclomatic complexity check. My friend Glenn Vanderberg has a great quote that bad developers will move heaven and earth to do the wrong thing. That the amount of ingenuity that poor developers put into making the problem worse is really amazing. If they just take half that ingenuity toward making it better, then the world would be a better place. But for whatever reason, that doesn't happen. So this being kind of a poor developer said, this is yelling at me about something that I don't completely understand. So, I know how to solve this problem. I won't write that code in Java. I'll just write it in JavaScript instead. So they basically wrote the same monstrous code on the front end in JavaScript rather than the back end in Java, but the architects outsmarted them because they had a cyclomatic complexity check on the JavaScript code too. And now this developer went to the architect in great frustration and said, this stupid code base won't let me check anything in, and that's the day they learned about the strategy design pattern. Now, I'm not suggesting that this is the best way to teach developers about the strategy design pattern, but I am suggesting this is a way, as architects, we can automate the governance around important things in our code base to make sure that really bad stuff is not showing up using metrics like cyclomatic complexity and effort and effort coupling and distance from the main sequence and all those code-specific metrics that we have. The problem, though, with things like cyclomatic complexity, well, cyclomatic complexity is a great example of this because it's a very blunt instrument. What cyclomatic complexity can't tell you is the complexity I'm looking at, is it essential or accidental? Because some problems are legitimately hard, and some problems are just made hard by bad coding. And cyclomatic complexity can't distinguish between those two things. So we have very blunt tools for assessing architecture from metrics and other similar traditional verification methods. But that brings me to an interesting place, because one of the common requests I get as I talk about fitness functions is they look at this and go, hey, that's kind of cool, but it's really limited. Because this is a compile time metric. This only works for a single compilation unit, which is nice and all, but what I really want is that, but for my microservice communication. That's what I want to check, is can I write rules about how my microservices communicate with each other, because that seems genuinely useful, and it is genuinely useful. Here's the problem. What are those things written in? Is it microservices? They may be written in one thing, they may be all written in something else completely. What kind of database are these things using? Are they using the same database or different databases? Is that going to have an impact on the way that I govern this? What kind of communication protocols are they using? Because it could be synchronous or asynchronous. Are they in choreography or workflow? If they're in choreography, the domain services have to know a whole lot more about the workflow. The problem is there's no such thing as a generic architecture. Every architecture is this huge snowflake of all these different moving pieces that is sort of not proactively organized in many cases. It just sort of grows like weeds. And a lot of architects look at this and just give up hope. Because they're and this is a kind of a weird sea change, because when I joined ThoughtWorks many years ago, open source was all the rage. And it was actually really difficult to get developers to stop writing new open source applications. Everybody was writing their own framework. Remember when everybody was writing their own web framework for a while, and then everybody was writing their own Ajax libraries for a while, and then everybody was writing their own dependency injection for a while? All these different, now the JavaScript world is still, to a degree, doing that. It's sort of shifted now where I keep seeing architects that if you can't download a perfect tool and get it to work by setting 4 or less configuration parameters, I don't care about that. I'm not interested in that. And there seems to be this attitude that you either find something that's purpose-built for you, or you have to build some massively complex thing from scratch. And neither of those things is true. And in fact, for most fitness functions, the first question you have to ask yourself is the information I'm interested in available somewhere? And the answer is, of course. I can impose observability on all these services and find out who they talk to. And now, with 10 or 15 lines of scripting code, probably not even in the same programming language I'm writing my services in, I can gather up log files, I can look at monitors, and piece together, are these things talking to one another correctly or not, and build my own very specific metric for the thing I care about in my architecture. This, I think, is the road forward, is not the general code metrics, because general code metrics are great. They tell you if code's complicated or not, but it can't tell you if it should be complicated or not. Only your problem domain and your judgment can do that. And so what I'm suggesting is that we need to stop looking for these universal metrics that are going to replicate mechanical engineering and calculus and all the tools they use, and instead start looking for hyper-specific metrics for your hyper-specific architecture. Buildings are pretty generic. Software is a lot less generic than buildings and bridges. We build a lot more variability into those things because we can, but that makes it less and less likely that we're going to find a single analysis technique that allows us to do that kind of analysis. So let's talk about some of these things. And part of this is this idea of having tools to assist you in doing very specific things. So I want to show you a couple of examples from Software Architecture, The Hard Parts, which is the book that Mark and I wrote a couple of years ago now, shockingly. And one of the things that we talk about in Software Architecture, The Hard Parts, are these decomposition patterns for taking a monolithic application and moving it to microservices. And you don't just do this in one fell swoop. There's a whole process that has to be done there. And I'm not going to go into all the details here because there are a lot of them, but here are all the steps that you go through in this process of doing component-based decomposition. I want to talk about a couple of these because they highlight these kind of very specific fitness functions that I'm talking about here. So one of the things that you do in this world is flatten components. And the idea behind flattening components is that there is an unfortunate circumstance about the way that we define components in major platforms like Java and .NET, because we also use that to define namespacing for the components. And the weird side effect that you run into needs you to flatten components. So flattening components is this idea of taking like components together and then reorganizing them to actually make them components and not just namespaces. So when you look at names for components like this, you see this hierarchy of app, dot, dot, dot. And of course, this mimics a directory structure in that world. And so let's say that you have some classes that look like this, and you have this letter component here in your ecosystem. So there's customer, and it has inside it billing, notification, there's notification SMS, and other notification classes that do some other stuff. The problem you're running into here is these are not well-defined components. These are namespaces, but they're not components, because you have things lurking around at non-leaf nodes. If you really wanted everything to be a component, all the code would be at the edges and it would be a pure hierarchy, but we have some of this stuff lurking around at the customer level, and sometimes you design code like that because everything under that can automatically see it, so it lets you cheat on scoping, but it messes up your component hierarchy. So those are those customer profile classes that are just sort of floating around at the base level of this package. And the idea of flattening components is going through a process of saying, okay, well, let's get these things into places that we don't have intermediate code and we have a pure hierarchy. And those customer would be customer profile. And so now I have an actual where all the code is at leaf nodes. That's that idea of flattening components in an architecture like this as you're doing a migration. And here's an example of a fitness function to help you to do that. And this is where I was getting to, is the fitness function to help you do that. Once you've done this exercise of reorganizing all these components, you want to put a fitness function in place that says, as I start reorganizing things again, none of these start leaking into places where they shouldn't be. So this helps you both the process of untangling it, but it also allows you to lay in governance after the fact to make sure that once you fix something like this, it doesn't come back to haunt you and bite you later. So you identify root namespaces and fail the test if there's any source code in that namespace. This is an easy test to do in something like ArcUnit or a NetArcTest. And it lets you make sure that once you have done the work to isolate these things, they stay isolated and don't break. And this is an example of this kind of hyper-specific metric. I'm doing the structural change in my architecture, and I need to make sure that this part that I put there doesn't break. You know, a lot of woodworkers use little wedge-shaped pieces of wood to jam in between two things when they're gluing them or clamping together, and that's exactly what this is that kind of hyper-specific little wedge of wood that you slip in somewhere like that. The other example I wanted to show you here is analyze component dependencies, which is another step in this process. Once you've gotten all these things flattened, you want to analyze the dependencies between these things. So, for example, ticket creation assigns, to go to ticket assignment. And there are a bunch of different ways you can do analysis. I don't want to talk about the analysis per se. Other people will talk about some of these analysis techniques as we go through the couple of days here. I want to talk about the fitness function that comes out of this. This is using a tool called X-ray to do analysis on code. This is an example of a really terrible code base where each line represents connection between classes, and the bolder the line, the more connections there are between them. So this is a classic example of a big ball of mud that you don't want. And so this is a good example of a way to put some governance around that. Now, whether this is 6 or not in your ecosystem completely depends on your ecosystem, because you may have a bunch of really intense inheritance relationships that fit in your problem domain, and you want all those to be preserved. But again, this is a very hyper-specific kind of metric that applies only to a very particular kind of code base undergoing a particular kind of engineering process. And of course, you can, once you've identified those things, you can create tools to say that these should or should not have dependencies on each other. And again, very specific. Here's an example, in fact, in ArcUnit for a component can't access, a component A can't access component B. You can define these rules programmatically in these fitness function design tools And here's an example in C#. So all those possibilities exist in this world. And the last of these that I want to talk about is create component domains. We want to create domains from these things and build out domains for each of the chunky parts we're going to do for our migration for this architecture. And here we can create a fitness function that says, once I've established these domains, make sure those domains stay established. And again, to make sure that you don't end up with stray code somewhere that it shouldn't be. So this is helping you with the structural migration of your code base. And there's an example of that in ArcUnit for Java. So let's talk about the last section here, which is called impact. This is an unexpected use of fitness functions for determining things about software architecture that, again, goes toward this idea of hyper-specific metrics. So we wrote the first edition of this book in 2017, and it went out into the wild. And a lot of our colleagues started using this technique of fitness functions. And when we started to write the second edition, we solicited all of our coworkers, hey, what have you done interesting with fitness functions? And we got a whole bunch of these examples back of using fitness functions as an experimental media. So let me show you what I'm talking about here. This is an example of where a client had a monitoring service where they were taking in these batches of messages from electronic transfer, and they were getting translated through this monitoring service and then ending up in their ecosystem. So this is a big giant import job of all these documents. And they noticed that somebody's job at this company was to take the messages that didn't translate correctly and manually do some manipulation on them to fix them. And so at some point they asked the company, how many of these messages fail like that? And they said, it's not many. We think 10 or 15%. Like, have you ever measured? It's like, no. So we did. We set up a mock service to measure. It turns out 40% of the messages were getting kicked back because of bad data or bad relationships, et cetera. This is a major problem. That's why it's been taking so much time, because their data is terrible. And they just never realized it. They just sort of been putting a Band-Aid on it every day for months and years of, oh, well, this is just a part of our ecosystem. Until you actually measure the thing, you don't know. And this is a perfect example of there may have never been this completely unique combination of technologies ever implemented before, and it's hard to know until you start measuring things. So lots of messages come through there, what happens when they fail, and then after the fitness function, we determine that it's a 40% failure rate, which is obviously not good. Here's another one. This was a case where we're getting a number of requests from a legacy system, and the team did sort of a back-of-the-envelope calculation that, okay, for auto-scaling these messages, for this integration point, we think it's going to be about 120 requests per second. But then we started getting a lot of failures and timeouts and other sorts of reliability and availability issues. And so they created this fitness function. Calculate the number of incoming calls to verify the max requests, create a new relic query and load them and monitor the stress point and put that in the pipeline to guarantee availability. It turns out that when you actually measure it, it was an order of magnitude higher. It's 1,200 requests per second is what they needed. And this is a perfect example of them going back and saying, 1,200, there's no way. It's like, oh, well, but this one actually multiplexes into 4, and oh, this one, oh yeah, and when that happens, a whole bunch of messages come from there, and it's like, yeah, it probably is 1,200 requests per second. But in software architecture, you're very often building something that's literally never been built before. We've never built this kind of service on top of this legacy AS400 with this kind of legacy database before. But we need to measure it, and we need to find out stuff about how it actually works so that we can make estimates, but then validate those things so that we know what's actually going on. This is one that's so common that we've given it a specific name, a fidelity fitness function, because it turns out we keep having to do the same thing over and over and over again, which is, the scenario is, and this is going to sound super familiar to many of you, we have this terrible, old, crusty system that's critical to our business, and we've tried to rewrite it like 5 times, but now we really, really need to rewrite it in some sort of modern technology. But it's both so convoluted, we don't really completely understand how all that code works, but major markets depend on that behavior. And the new one has to produce exactly the same results as the old one. Okay. So this idea of a fidelity fitness function, there's the conclusion, is this idea that for whatever old feature you're deprecating, you put in at the choke point where you decide, am I calling the new or the old? You put in a fitness function that says, call both of them and validate and make sure they match. Now, the way this normally works is the reason you're getting rid of the old system is it's really slow. And so initially you set it up so it calls the old mainframe and then calls the new code and returns the mainframe code because that's still the source of truth. But then as you get closer and closer, you can swap those and get better performance, but still validate in the background until you're convinced that both those things are going to match, and then start tackling the next chunk of behavior in that existing system and slowly rinse and repeat until you've isolated all those cases. I've seen a lot of companies try to avoid this because it's a real pain to set this kind of ecosystem up, but then they do the entire, I've seen several multi-year projects where you get to the end and you turn the switch on the new one and it's like, it's not the same answer. And we don't know why, because you don't really know how the old code works, and so you have to have this at some point. And so this was the conclusion for this team. It was useful not only because it allowed them to piecemeal move this ecosystem from one place to the other, but it also helped them identify a bunch of data that wasn't actually properly mapped, because this is where the rubber meets the road and they actually have to use this to do real work. They found out gaps in their analysis by doing this because they're testing real things as it's happening in real time. So let me give you one last example of essentially the same mechanism, but it's a great example of how really specific kinds of metrics can enable you to do magic tricks. So a lot of developers and architects are really nervous about really aggressive agile engineering techniques like continuous deployment because they think it makes things too risky. It turns out, though, that to be able to do continuous deployment, you have to figure out ways to mitigate that risk. And here's a great example. This is a case study from the GitHub engineering blog called Move Fast and Fix Things. GitHub works at extreme scale. One of these engineers said that every time they roll out something new, their boundary cases happen almost instantaneously because they're operating at such high scale. But they're also a very aggressive agile engineering organization. They do continuous deployment. Every time a developer makes a change, it goes through a deployment pipeline, goes live. They average 60 deploys a day at GitHub, and this described a problem they had about merging things. Turns out since day one at GitHub, the way they've merged things is to take those two files and drop out to a command line, tell command line Git to merge them, and then suck it back into GitHub. And that works perfectly, it just doesn't scale particularly well. And as I said, they operate at really high scale. So they finally accepted the inevitable and wrote their own in-memory merge and tested it against the Git spec. But now here comes the scariest part of my whole talk. Now they've got to put it live. But here's the problem. You can't break merge at GitHub. It's literally never had a bug logged against it. And the last thing you want to do is roll out some change and start having bugs show up in merge. But that's not the real fear that you all have in doing this. The real fear that you have is you're going to roll out this little change to merge and something way over there is going to break that you didn't even realize was attached to that code until you go back and say, oh yeah, this is, okay. That's the fear that keeps people from doing this kind of engineering technique. What GitHub did to mitigate that and open sourced it so you can take advantage of it is to create this tool called Scientist. Scientist was originally written in Ruby on Rails, but it's been ported to more than a dozen other languages now. And what Scientist allows you to do is conduct experiments at the architectural level. It creates these experiment blocks with two clauses, use and try. Use is the old code you're getting rid of, and try is the brand new code you're trying out. Every time it hits one of these experiments, it always executes use, and that's what it always returns to your user. So you never get a surprise answer back from this query, but you can also set a threshold for how often it also runs try. And for merge, they set it for 1% of the cases, also run try, and when that happens, it randomizes the order in which use and try are run, measures the duration, compares the results of try to use, swallows and records any exceptions, publishes all this stuff to a dashboard like this. You can see at 2:20 a.m. they were doing a little over 2,000 merges within that minute. If you zoom in on the bottom, here are the errors in their new code. But none of this has impacted any users yet because this is all happening underneath this experiment block. At the same time, they're measuring performance. The green line is the new performance and the blue line is the old one. They ended up running this experiment for 4 days until they had 24 hours with no mismatches or slow cases. Over the course of those 4 days, they did more than 10 million comparisons between use and try until they had really high confidence that it was doing exactly what they wanted to do. This is an example of a fidelity fitness function, but an example of one of these hyper-specific metrics. And I think that's where we're going to end up in our industry, are these really highly specific metrics that apply only to our unique circumstance in our project, applied on a regular basis with a fast feedback loop. This is the secret, I think, to actual software engineering to get us to the place where the other engineering disciplines are. That's it. I'm happy to answer any questions.
All right. So checking the Whova app, we already have a lot of questions. Let's start with the first one. Do you use fitness framework as Arc Unit?
I'm sorry, what about Arc Unit?
Do you use fitness framework as Arc Unit?
Yes, I use Arc Unit all the time if it's a Java project. There's a NetArc test if it's a .NET project. But, you know, Arc Unit is really magical because you can do these kind of structural checks against your code. And I often get a question of, well, what about my exotic language X unit? Or CPP unit, or JavaScript. Where's Arc Unit for JavaScript? A lot of the linting tools. So the linters are actually parsing all the code for you, and they're handing you the abstract syntax tree. You can write rules about code structure in linters, like ESLint or CPP-lint or PyLint in the Python world. And so even if you don't have a dedicated framework, you can still do structural checks on your code using linters, because they're actually doing the hard work for you, which is parsing all the code and just handing you the abstract syntax tree to make some rules about.
Thank you. Another one. Is there a generic fitness function or modal applicable at top level to any system?
A generic fitness function applicable to all systems? No. I mean, it's like asking, is there a unit test that's applicable to every single system? I'm trying to think, is there a unit test that you would apply to every single system? I can't think of one off the top of my head. You might say something like security, but Rebecca has a great example of an application that didn't need security. They built a little sandwich ordering app for their office, and the worst thing that would happen if there was a security breach is you'd find out that I ordered the same kind of sandwich every day. So that application didn't need security. So, but it's like saying, you know, it's again trying to treat software as something generic. You know, we build copies of the same buildings all the time. We never build exact copies of the same piece of software because we don't need to. It's digital. You can just make as many copies as you want. Physical buildings are physical buildings, so software is much more bendable. So it's a lot less likely to say there's one thing that's universally true, I think.
Okay. Do you think AI would help to understand input-output of legacy systems and help to create a FF?
The inevitable AI question. So get ready for a lot of these this week, I suspect. That is, in fact, one of the places I think that AI is going to be tremendously useful for software developers is translate this terrible COBOL code into something we can understand. We actually have some developers who do that now on projects when they're trying to untangle these legacy code bases. The problem with that, though, is that it's going to lie to you a lot because it can't execute that COBOL code, and in fact, it doesn't have any logic. What it's going to tell you when you ask it that question is the statistically most likely next word. And probably 80% of the time, that's going to be true. But it's going to be hard to tell the other 20% when it's not. So trust, but verify for anything that comes out of an AI. So this is a great example of, this actually came out on the most recent edition of the ThoughtWorks Technology Radar, the kind of second order effects that AI stuff creates. We have an entry on our radar that talks about using dependency management to avoid package hallucinations. So you can imagine a scenario where people keep asking ChatGPT for some sort of JavaScript behavior, and ChatGPT just hallucinates a package dependency. Clever hackers could say, hey, it keeps hallucinating that package dependency. I'm going to put some real nefarious code behind that package dependency and just slurp that right into projects when they use ChatGPT to say, hey, here's some magic. And now all of a sudden you've got an attack vector that you never really anticipated. You need to do dependency checks on package dependencies suggested by AI, or you're opening up a massive attack vector that people will be able to take advantage of. So there are so many of these second order effects that are going to come around as we start using AI aggressively that we're going to have to figure out as we go.
Thank you, Neal. Another question. Where do we keep run this fitness functions, test cases, package, Lambda function, separate microservice?
Great question. As quickly and as aggressively as you possibly can. One of the lessons that we've learned about software development, it goes back to what I said before. Modern software consists of hundreds or thousands or millions of discrete little moving parts, almost any of which can be changed in an arbitrary way at almost any given time. Every time you touch that code, you potentially break some little connection somewhere. You want the fastest feedback possible to say, have I actually broken something? And the faster you get that feedback, so the problem you run into if you don't have fast feedback is, I've just committed this code that broke this little thing. But I'm not going to validate this because it's too hard to validate for a few weeks until we do a big test. But now there's 2 weeks worth of stuff that's happened. Oh, great. Now I've got to sort through 2 weeks worth of stuff to see what broke that little thing, versus if I can make that little change and then validate, I can find out exactly what broke because that's the only thing I changed. This is exactly the same dynamic that you see with continuous integration versus big bang integration. Not only is continuous integration easier on a daily basis, but you literally do less merge work on a continuous integration project than you do a big bang integration project. Because in a big bang integration project, what you're allowing to happen is that every change gets tangled up with all the other changes, and the last thing you have to do is untangle all those things to get them all merged together. Whereas if you integrate every single time you change, there's never this massive complexity that you've accidentally built up. And so it's the exact same thing with any kind of change in software. This is why I say this is the fundamental lesson that Kent Beck taught us back with XP. The real secret to engineering and software is incremental change and fast feedback as fast as possible. So to go back to your question, you want this in continuous integration, you want it in deployment pipelines, You want at the earliest possible opportunity you can validate whatever that change is, because the faster that feedback loop is, the faster you can react to it and fix it and move forward and accelerate your software development.
Thank you. And fitness function can be enforcer, enforce some rule, and as well observer, find rec sec in certain service kind.
Is that a question? Say that again?
Fitness function can be enforcer, enforce some rule, and as well observer, find rec sec in certain service kind.
I'm not sure what the question there is that you're asking.
If you can clarify your question on Hoover app, that would be great. Okay, let's move on. So apart from model and structure, how does infrastructure fits in these fitness functions?
Well, you can use, I mean, a lot of what you're going to be doing is validating infrastructure capabilities. So part of your infrastructure, well, it depends on what you're talking about for infrastructure. You're talking about the deployment platform, or you're talking about the developer infrastructure. Both those things are applicable, because your deployment platform, you need to check scalability, performance, et cetera. And that's exactly what fitness functions are designed for. But even in things like deployment pipelines, so if you're spinning up containers automatically, you should run fitness functions on them to make sure that they got instantiated correctly. That, for example, the observation port is active and broadcasting, and that security things are in place, and that the latest package dependencies have been applied to that container. And so there are a number of fitness functions you can use for infrastructure validation as well as architectural validation. But, I mean, this is really just a way to get more feedback loops closer to the metal in software. You call them fitness function, you call them unit tests, you can call it whatever you want. It's just a way of building verifications to get faster feedback for all the parts, all the moving parts of software. It's more important now for infrastructure than it ever was, because our infrastructure is more code-based than it was before. So, you know, anytime you're executing code, it's probably worth having some sort of governance in place. Because that's really what fitness functions are, is automated governance.
Okay, and last question for the session. Assuming we have defined a great fitness function, how do we iterate and improve our architecture? Do we change it manually, or are there tools that can change the structure of our project with the aim of maximizing our fitness function?
No, there's no magic. If there was a tool that did that, I would be the richest person on earth. Having created that, I'd be flying around in a jet, I'd be buying social media networks. There's no tool that does that. But I mean, these are living parts of your code base, just like unit tests. You never ever hear a developer say, oh, we need to change that code, but we'd have to change the unit test, so we can't change that code. That's crazy. Of course, you change the code, you change the unit test. Same for your fitness function. We need more scalability. Oh, we've got a fitness function there that yeah, you just change it. It's a living part of your code base. So it lives and breathes. These actually change a lot less frequently than unit tests and functional tests, because the thing that changes the fastest in your software is the thing you're writing the software about, your domain. And capabilities change less frequency, and ecosystem changes even less frequently than those do. So it's not like you're constantly running around chasing these things broken. But what you are doing is putting these things in place so that when an unexpected little thing breaks somewhere, you're not dumbfounded by it a week later because nothing works. You see it as soon as it happens, and you fix it, and you move forward. That's really the secret to effective software development, I think.
Thank you very much, Neal.
Thanks.
We are truly delighted to have you here with us. Thank you.